formula? Because I know you said you were going to give us the
I'll give it. Yeah, the average kinetic energy formula I'll give also.
and the URMS.
Yeah, and the URMS. So you don't have to memorize it. You just have to be able to.
And what about the
Like it is.
non-ideal?
Non-ideal, I'm going to give that to you too. I haven't talked about non-ideal gases yet, but I'll talk about that pretty soon. Okay. After you guys deal with ideal gases, then I'll talk about some non-ideal stuff a little later. In the homework, I mean. After you deal with it in the homework. Okay, other questions?
The base is only hydrolyzed, right? But what about the strong base? Is it ionized or hydrolyzed?
Strong bases hydrolyze. Strong bases do not either. Hydrolyze only.
So base only hydrolyzed?
Bases only hydrolyze.
Because I got confused when you say like strong bases only. Well, strong bases do not hydrolyze. You said that in base.
Yeah, strong bases do not hydrolyze. Strong bases only ionize. Let's take a strong base, sodium amide. How does that only hydrolyze? A lot of people say, well, it's a strong base, it ionizes. So what would it ionize into? Sodium and amide, right? But that's not what we call a strong base, because that's what we call what? I don't call this ionization strong base ionizing. I call this a what? You guys looked in, do you have this in your notes? I hope you have this in your notes because I did this one as an example. You know, the thing is, it's very hard to remember and memorize things just seeing it once. You know, it's a repetition unless you have a photographic memory. You know, one of the reasons I call roll every day because I have a hard time remembering names. The only way I get the names down is if I do it every day, and then it'll stick, right? If I don't do that, forget it, you know. I can't just call your name once at the beginning of the semester and then on the exam day be able to recall everybody's names because I got over 70 students, right? That's the only way I can do it. Otherwise, I can't remember names. And I got to remember names to tell you to wear your goggles or do whatever else. Right? But, you know, I can't believe the number of people who think they can see it once and then feel confident for the test. I mean, I would feel totally uncomfortable going into the test only seeing something once because I'd feel really, really shaky. You know, I'd feel really, woefully underprepared, you know. And so that's why the repetition thing. I don't call this a strong base, I call this what? Yeah, this is a strong electrolyte. Well, strong base is a strong electrolyte. I called it a soluble salt. This is a soluble salt. Sodium salts are soluble. And what are we left with? This is amide. Amide, look on the chart there. Is amide the strong base? Yes, this is the strong base, amide. So what do strong bases do? We know this is a strong base. How do you ionize this? Did you try it? Lots of people do try to ionize this, and I've seen very bizarre species on ionization. I've seen H plus NH. You know, I've seen things that don't make any sense, like the charges don't add up. But let's say this person got the charges right. This would be an H plus NH2 minus, you know? Do you think those species are stable? No, I mean, this is supposed to ionize completely. It's going to go, there's a big driving force for this, it's going to go 100%? No way. So how do you ionize that? How do you ionize? You don't. You don't. I don't know if you tried. Take every single base we've encountered and try to ionize it. Just try to ionize it. Carbonate. Carbonate's a base. On the chart there, do you see it? It's, you know, on the right hand, it's moderately strong, weak base. Ionize it for me. Take every single, have you guys looked at the acid chart and looked at all the bases, read them? Remember what I said about this? Read them once in a while, once a week. You take every single base there and you try to ionize it, you're not going to ionize one of them. Impossible. Well, it is possible. People do it all the time. They come up with the weirdest stuff. This would be good. At least they got the charges right, and at least these species seem reasonable. I've seen ridiculous things like, NH plus, H plus. This can't be. I mean, 2 pluses equal a minus. This is impossible. And so I've seen. When I ask for this is more, you get more of the bases in Chem 1B than you do in Chem 1A. And so, it might not click 100% here, but, in Chem 1B you do so much with bases that it becomes second nature. Okay. And so the answer is, do strong bases only hydrolyze? Yes. They only hydrolyze. They do not ionize.
Is that all bases or strong?
All. Even weak bases. Well, just try it. Just try it to prove it to yourself. All of them. Strong and weak. Okay.
So,
Yeah. Any other questions? So how does it hydrolyze? You should have this in your notes too. You've probably seen it a bunch of times, right? Amide plus H2O yield, ammonia and hydroxide. Hydroxide is the strongest base that can exist stably in water. All right. If there are no other questions, then tomorrow's lab, we're going to use some updated equipment. And the previous lab relied on something called a CVL system, where you take a TI-83 and use a program called Chem Bio, input the data. We aren't going to use that. The new system is called LabQuest. It's like like an iPad or PDA type deal, where the interface is graphical. And so setting up data, what we call data acquisition, is really simple. You just put the numbers into the field, and it pretty much self-recognizes the probes. And so we'll talk about that. So when you do your notebook prep, you're only prepping for water plus water. Cold water and hot water is what we're doing tomorrow. Just experiment 1. And then the remaining experiments we'll do on Thursday. But for that first experiment, you don't put in any of the TI stuff. TI-83, punch this button, punch that button. We'll take a look at it when we're in lab tomorrow, what you need to do for setting up for data acquisition. Is that clear? Uh-huh.
the last lab is tomorrow, right?
The last lab, which is experiment 18, usually you have a week to do it. But the last lab would be the KClO3 lab. The KClO3 lab wouldn't be due tomorrow, it would be due on Thursday. Yeah. The KClO3 lab, you can just fill in the report sheet in the lab manual. So let's have that due Thursday. The KClO3 decomposition lab. This is an unknown mixture problem. The mixture contains some KClO3 and some inert stuff. And so we don't know what the percentage KClO3 in this mixture is, but the only thing that will decompose is the KClO3. And so we have KClO3 plus inert. ingredients, something like that. And so we need to figure out, how much is it? Maybe it's pure KClO3, if you get 100%, or maybe it's not. And so you do those calculations. The calculations, the thing that takes some time is the interpolation, the double interpolation or triple interpolation we had to do for the barometer correction. And then the vapor pressure of water, the interpolation for that. But the remaining calculations are not too bad. Okay. So due Thursday, the KClO3 experiment 5. And this is not a formal report, it's just fill in the blanks on the report sheet. Experiment 18, that one's going to take some more time to work through, so you'll have an extended due date on that. I'm going to talk about it tomorrow. Experiment 18 at the beginning of lab, how you're going to do that. And then that'll be due next week. All right, other questions? Well, let's talk about what we're doing tomorrow in lab, because we're in the right section, chapter 7 for this. I'm behind schedule. Find a decent pen here. Tomorrow's lab involves calorimetry. Let me see if I can get a decent. All right, in calorimetry, we have a few of the system. And the system, tell me all the options we have on the system. Open, closed, isolated. And so open, closed, isolated. And then, what else? Typically we work with what type of system? Closed system. And so only energy is exchanged with the surroundings, so closed system. And then
The closed system has a constant volume.
constant volume or
Constant pressure.
constant pressure. And so we have this constant volume or constant pressure. And so we have two types of calorimetry. There's constant volume calorimetry, which is often called bomb calorimetry. This is bomb. And there's constant pressure calorimetry, which we call coffee cup. Because that's how we're going to be doing it, using coffee cups. This is heat of the system, the heat of the system. So, let's say it's an exothermic reaction or something. Actually, there's one more. You're missing something here. What else can a system be? There's two more options we have to select.
Object or reaction?
Yeah, object or
Reaction process.
reaction or process, and that's important. Object or reaction / process. The reason it's important is because of this. An object sticks around. The only thing objects can do is you can warm them up or cool them down. Reactions, on the other hand, are finite. They have a certain lifetime. So there's a chemical reaction, it releases heat. Once the reaction is over, then is there any more heat produced? And then what happens to the system? Once the reaction is over, the system is gone. And all that heat goes into what's remaining. What's remaining is the surroundings. And so this is, object and reaction or process is very important. Well, the Q of the system is going to be the opposite sign of the Q of the surrounding. Q of the surroundings here we call the calorimeter usually. Calorimeter or calorimeter plus. It depends on how we deal with it. Sometimes plus other stuff. So in tomorrow's lab, experiment 2, this is the first experiment we're going to do is this. We're going to have hot water in a coffee cup like this. The coffee cup is going to be thermally insulated styrofoam. We're going to put 2 cups so that we have increased insulation. And then we'll have a lid on top of this with a little hole here. The hole is going to be cut for a temperature probe. We aren't going to use thermometers here. We're going to use these stainless steel temperature probes that will go inside here. And inside here, there's a temperature-sensitive material. And they have different types of probes here. And then we're going to put in 50.0 milliliters of hot water. Hot water. Unfortunately, what happens to the hot water? Does it stay at a constant temperature, or does the temperature drop? The temperature drops. So time is an issue. I mean, for example, if you measure the temperature, a minute later, the temperature is going to be lower. And so what happens is we measure the temperature, and then you got to pop off the lid and mix in stuff in here. By the time you mix it, what happens to the temperature? The temperature decreased. But is the temperature decrease in a predictable manner, or is it just random? Is it just a smooth, predictable temperature curve? It's not, unfortunately, it's not linear. It's a non-linear. But what we're going to do is we'll monitor the temperature. We'll pour in our hot water in here, and then we're going to monitor the temperature for like 5 minutes or something. And so what we want to do is we want to have like the time and then the hot water here, and then just see, at time 0, let's say it's at 70, 80 degrees, 81.5 degrees C or something like that. And then 1, 2, 3, 4, 5. What's going to happen is the temperature is going to decrease with time. That's something we can try to predict mathematically, but at the same time we're doing this, we have another cup here with cold water in here. And so we'll put in 50.0 milliliters of tea cold H2O liquid. And tea cold is just room temperature. It's not our 25 degrees C room temp, it's whatever the temperature of the water is. But the thing is, we want to measure that temperature, so we're going to have another probe in here. And so we're going to have 2 temperature probes here, one monitoring the hot, one monitoring the cold. And we're going to monitor these simultaneously. So this, because of the AC, it might be like 22.5 degrees C, let's say, inside there. Okay, is the temperature of the room temperature water going to change much during this period? No, it's going to stay pretty flat throughout. But we want to make sure it is. Maybe this is much colder than room temperature. It's coming out of the tap cold. And so we're going to monitor the temperature using a graph like this. Maybe I need this. Let me erase this. So here's our temperature, here's our time. Let's just start at 0, 1, 2, 3, 4, 5, 6. The cold water stays pretty much constant throughout this period, but the hot water, though, is going to decrease. And the hotter it is, the faster the temperature decrease. So as it cools down, the cooling rate slows down, like this. Okay, then at minute 6, this is what we're going to do. We're going to pop the lid off the cold. If I pop the lid off the cold, is the temperature going to change much for the cold? No. So I'm going to pop the lid off the cold, and this is a major change from your procedure. We're going to pour the cold water into the hot water. You know, your procedure says to pour the hot water into the cold. But if we pour the hot water into the cold, that's going to introduce an even bigger error, right? Because once we pop the lid off, what's going to happen to the cooling rate? It's going to accelerate, right? And screw up our data. And so we want to pop the lid off this for a minimum of time. And so you need a partner for this, and the partner is keeping track of the time on a stopwatch. And then they're going to tell you, as we approach minute 6, you know, we want to pop the lid off this, and then pour the cold water into the hot. Good. So at minute 6, the cold water probe is out. Now this is measuring, what is the T-cold probe measuring now? Air temperature, right? And so from minute 6 on, these are all air temp. But what's going to happen to the hot water? It's going to dramatically decrease. And so here, actually I should have blown this up. But we might see some fluctuations here, and this isn't the greatest curve here. Let me redraw this. Okay, now looking at the T hot, what's going to happen at minute 6 is this might be in or out, we don't know. Then you start mixing it. As you start mixing it, you can have what are called thermal gradients, where there are parts of this. Now this is 100.0 milliliters. There are parts of this that are cold and parts that are warm, but eventually it'll settle down. Once it's thoroughly mixed, we should get a nice cooling trend like this. And so what we want to do is we want to ignore these points because of incomplete mixing, and focus on these points. Okay, once it's thoroughly mixed, then what we can do is we can back extrapolate this. As we back extrapolate this, this is the cooling curve of the well-mixed mixture. And we back extrapolate this to 6 minutes. And so what we're going to do is we're going to completely ignore this data point at 6 minutes because this data point is not accurate. Our real temperature should have been here based on how the cooling curve, it should be a nice smooth curve. So we're just going to hand draw that in there. Does that make sense?
Yeah.
All right, and then we need to know what was the temperature of the hot water at the time of mixing. At the hot water, what we're going to do for the hot water is we're going to forward extrapolate it. Because we didn't actually get a measurement there. We're just going to say this cooling curve would have just continued on here. And even though our probe measured this temperature, this has got to be the T hot at the time of mixing. And so at the time of mixing at 6 minutes, this is our hot water temperature, T hot. This is our cold water temperature. Oh, no, that's not our cold. This is T mix. And our cold water temperature is down here. Our cold water, now this is probably measuring air, right? This is air. Air could be warmer. But our cold water temperature, we would extrapolate this out, forward extrapolate. And wherever it intersects, that's our cold. All right, so we're going to collect a lot of data just to get 3 temperatures. The 3 temperatures that we need are the temperature at the time of mixing. You know, what the hot water was, what the cold water is, and what the mix is. Okay. Now, what are we going to do with these? Well, we're going to do some calculations here. So let's talk about the calculations here. This one, the system and the surroundings, be a little bit complicated, maybe. Okay, so let's go ahead and define. What do you want to call the system? The hot water, the cold water? What do you feel like calling the system?
The hot.
I would like to call the cold water my system. Why that is because the surroundings has to encompass the rest of the universe. And so, if I have the cold water, 50.0 milliliters, and the surroundings will be the hot water, coffee cup, lid, temperature probe, air, rest of the universe. And this is what I'm going to do because hot water, it's easy to do temperature calculations. The coffee cup, do we want to figure out what the specific heat of the coffee cups is? Like weigh them and figure out how many calories per gram of coffee cup? Does it seem reasonable? No. Or the temperature probe? You know, do you want to weigh the temperature probe, figure out how many grams the temperature probe weighs, and then figure? It would be much easier to treat this as moles. Do you want to figure out how many moles of stuff we have? No, it would be better just to treat the whole thing as an object. And so all of this is one object. And this object is called one object, and it's called the calorimeter. And so what's going to happen is this. The hot water in the hot calorimeter is going to give heat to the cold water. How do I know the calorimeter is hot? Because it's in contact with the hot water. So it's got to be in some thermal equilibrium. It's been in contact for 6 minutes or more, right? And so that's it. And so our calculation's like this. Q of the system is equal to minus Q of the surroundings. And so Q of the system is Q of the cold water warming up. All that heat came from what? All that heat that warmed up the cold water came from the surroundings, which consists of the hot water plus the calorimeter. Now the first part of this is this. These 3 things are objects. Cold water is an object, hot water is an object, and the calorimeter is an object. When we're dealing with heat for an object, then the heat involved is equal to the amount of the object times what? C times delta T. And so what we need is we need the amount of cold water times C of water times delta T of the cold water. This equation is different than the one in your lab manual. It's different than the one in your lab manual because of the change in the procedure. Change in the procedure. Not everybody, you know, the department, not everybody wants to change the procedure. A lot of people like it when you pour the hot water into the cold. So this is, but I personally don't like that. So this is my personal. Otherwise, if everybody agreed, we would have changed it. Anyway, we're going to the Q hot. What is the amount of heat lost by the hot water? It's an object. Tell me. It's going to be the amount of hot water times C of water times, yeah, the temperature change of the hot water. This is the amount of heat lost by the hot water. Now, how much heat was lost by the calorimeter? Well, no, we'll come up with an equation. It's an object. So it's always the same equation. How many calorimeters do we have? It's the amount of calorimeters times C of the calorimeter times delta T of the calorimeter. Always the same. The amount of calorimeters that we have is just 1. And so it just turns out it's the amount, since it says 1, it's just C of the calorimeter times delta T of the calorimeter. Now, what do we know? Do we know the amount of cold water? How much cold water did we have? 50 milliliters, or 50 grams, you know. Do we know C of water? Yeah, memorize. 4.18 joules per gram degree C. Delta T of the cold? Yeah. We get these temperatures. Delta T of the cold, this is just T of the mix, that's the final temperature, minus T cold, the initial temperature. Do we know the amount of hot water?
Yes.
Yeah. Do we know C of water? Yes.
Yeah.
Do we know delta T of hot? Yeah, that's just T mix, which is the final temperature, minus T hot. We know the amount of calorimeter, which is 1. Do we know the C of the calorimeter? No, we don't know this. It's an unknown. Do we know delta T of the calorimeter? Yes. That's just T mix minus T hot. It's got to be at the same temperature as the water. They're in thermal contact. And so the only thing we're missing is C of the calorimeter. You know what C of the calorimeter tells us? C of the calorimeter tells us how much heat leaks out of that coffee cup into the rest of the universe. And so if it's a big number, let's say C of the calorimeter is a big number, we're losing a lot of heat. If C of the calorimeter is a small number, we're losing minimal heat. You know? And so this calorimeter, should it be a big number or a small number? Should be a small number. The other reason I changed this procedure is because of the curves. A lot of people were getting errors. They're getting negative. Let's say they got a negative heat capacity. A negative heat capacity, what that tells you is that if you put a hot liquid in there, a negative heat capacity means it's not going to get cold, it's going to get hotter. And so if you put a hot liquid into it at room temperature with a negative heat capacity, the temperature should continue to increase rather than decrease. Is that physically possible? No. And so if you get a negative heat capacity, then something's wrong. Either there is an error in your calculation, you got to watch out for the sign, you know, or there was an error in your procedure. Well, the reason I'm having you pour the cold into hot is because most of the time it was an error in the procedure. You know, the calculations were fine, yet they're still getting negative heat capacities. About 10% of the class. Anyway, the other thing is if you carefully control, you know, for example, if your water is not too hot, if your water is really hot, then the error is more significant because when you pop that lid, it cools much more rapidly, you know. And so they tell you get it around 50, 60, 70 degrees, but if it's too, you know, if it's not hot enough, then you don't really get a lot of heat exchange going, and that could also lead to error. But with this, since we're pouring the cold into the hot, you don't have to worry about the temperature so much. You know, if the water's too hot, no big deal. Just go ahead and do it, you know. If it's too cold, then heat it up some more. Fortunately, this is just water. Hot water, I don't know. Should I make you wear your goggles for hot water, or do you feel safe enough?
Just try.
Hot water, you know, boiling water can cause, I never thought much about boiling water, but I got boiling water spilled. I was wearing boots at the time, and they got into my sock. And so it was at a full boil, too. Not just a smooth rolling boil, but a full boil. Spilled a bunch of it on my sock. It dripped into my, completely soaked my sock. And then by the time I got my sock off, I had second-degree burns on my foot and a tiny spot, just like a really, really tiny spot of third degree. Because I was wearing these heavy boots and it took some time to get them off. So watch out, you know, water has very high heat capacity, and so it can store a lot of heat, and when that heat's released, it can cause some severe burns. Yeah, then I was thinking, boy, sandals would be better in that case, or even barefoot and then just throw it. Because then, even with sandals with socks, you'd have to take off your socks, you know. At least if you were barefoot, the water wouldn't have soaked into the sock like a sponge and cause more severe burning than you predicted. No. The other problem is the broken glass in the lab and the chemicals, you know. There's a lot of chemicals that people spill on the floor that you don't want to pick up through, you know, skin contact. Right? And so, yeah, close shoes.
Professor?
Yeah.
How'd you spill that water on your boots?
How?
Yeah.
This wasn't in the chemistry lab. This was on a camping trip. I was on a camping trip. I had a pot of water, and there's no handle on the pot. You know, it's a little like backpacking type pot, and so there's a little clamp that you grab the clamp, and so I had a clamp, and it was full. It was a pretty big pot. It was full, and then I guess the clamp slipped. I wasn't gripping it tight enough, and then it spilled onto my boot. Yeah. But it was just car camping, so it wasn't too bad. I didn't have to hike out. Yeah. But I wouldn't have been able to. All right, let's try another example of this. Those were objects. Let's take a look at a problem where it's a process, you know. And so the next lab, let's see, what are we doing? Okay, we'll look at a couple of examples. One, we're going to do this. We're going to use our coffee cup calorimeter, again with a probe. This, and we're going to put in water here. I think 50 milliliters of water or 100 milliliters of water. Did someone already look at experiment 2? 100? Was it 100? No, I think it's 50. We'll just go with 50. All right, so this is going to be RT, whatever that is, here. in our lab. It's not 25 again, it's just whatever the room temperature is. The reaction we're going to do is we're going to take some sodium hydroxide, solid, and then dissolve it in water to form sodium hydroxide AQ. All right, this is a exothermic. You know, delta H is less than 0, so that means energy is released. So the sodium hydroxide is going to be, say, 1.98 grams of sodium hydroxide. You know, the more sodium hydroxide, the more heat is going to be released. So we need to know the amount of sodium hydroxide we're going to put in there. Sodium hydroxide is always difficult to work with. One, it's a huge eye hazard, right? Have you ever gotten sodium hydroxide on your skin? It feels very slippery. You know, it doesn't wash off easily. This feels very slippery. If you ever touch your eyes, it burns. Extremely bad. It can cause severe eye damage. So be careful with this stuff. The other problem with sodium hydroxide is it's hygroscopic. You know, it's so hygroscopic it deliquesces. Remember when we were talking about primary standards? Sodium hydroxide is not a primary standard because it doesn't have a reliable weighing form. The stuff is too hard to weigh. Do you know why it's too hard to weigh? Keeps absorbing water. It's not hard to weigh. You could weigh it, but you'd need to have something called a dry box. A dry box is this self-contained box with a very carefully controlled atmosphere in there. There's no water. And then it's easy to weigh. You know, it doesn't pick up anything because there's no water to pick up. But we don't want to have to use the dry box for a primary standard. So sodium hydroxide is a pain to weigh. So what you're going to have is pre-weighed sample of this. And so you'll bring up a watch glass. This is going to be on Thursday. You'll bring up a watch glass, and then she'll scoop in some sodium hydroxide and weigh it for you. By the time you get back to your lab bench, the weight has gone up, but you know this is coming out of the desiccator, so we know we should have 1.98 grams, and anything above that would just be water being picked up. Well, the problem is the water is being picked up. What's going to happen? Well, some heat's going to be released, so that automatically we're going to have an error associated with this. But it's all right as long as you don't. So anyway, don't pick up the sodium hydroxide until you need it. So timing will minimize the error. All right, so here what we're going to do is we're going to monitor the temperature. So here's our temperature, here's our time, and we're going to do the same thing. You know, we're going to monitor it. And then at minute 6, what are we going to do? We're going to pop the lid and, actually before minute 6. Before minute 6, we'll pop the lid open and scrape as much sodium hydroxide as we can get in there. You aren't going to be able to get it all because some of it will stick on the surface of the watch glass. The stuff that sticks on the surface of the watch glass, do you want to take a water bottle and wash that in? No, because we don't know how much water we have in there. And that's going to screw it up too. So either way, we're going to have some errors, but hopefully they'll be small. And so we scrape the sodium hydroxide in, and when we scrape that in, it starts to warm up. And what we're going to see is initially the temperatures are going to look like this until it's completely mixed. Once it's completely mixed, then we should see a nice cooling curve, right? Sometimes the mixing process is a little bit slow, you know. You got to mix the solid and with the water. Because it's slow, the data collection, the lab says to collect 13 minutes worth of data total for each run. I sometimes, that's not enough. It depends on how slow it is to dissolve. And so I recommend for all of them, including the water, to take 15 minutes worth of data. So we're going to change it. And it's only 2 minutes more, so it's not going to be that big of a deal. But from now on, we're going to collect 15 minutes of data at 1 minute intervals. With these lab class systems, we could take data at much finer intervals. Maybe I'll change that too. But, I'm not going to change it this semester though. Future. So, do we ignore these points here? Yeah, we ignore these because we'll just call it incomplete mixing. So what we're going to do is we're going to focus on this. Time 15 minutes later, it should be pretty well mixed. Actually, it's not 15, it's 9 minutes later, it should be pretty well mixed. And so we'll look at the curve here and then just back extrapolate this to 6 minutes. And so this would be T mix here at 6 minutes. This should be T cold down here. We forward extrapolate this to 6 minutes. This is T cold. So what do we want to call the system? What do we want to call the surroundings? All right, why don't you take a few minutes and then you come up with your system and surroundings for this here. Give it some thought of what you would do. System would be sodium hydroxide. Surroundings would be cold water, and that's it?
No.
Okay, so that was quick, that's good. Q of the system is equal to minus Q of the surroundings. System is sodium hydroxide. Surroundings is
Cold water
cold water
plus air.
plus air
Or the calorimeter.
plus the calorimeter.
Well, it includes the coffee cup.
Okay, the calorimeter includes the coffee cup, the air, so let's eliminate the air.
Yeah.
And just say Q cold water plus calorimeter. Okay. So what is Q of the sodium hydroxide? Amount 1.98 grams times C of sodium hydroxide times delta T. Well, let's stop here. What is delta T of the sodium hydroxide? Would it be T mix minus T cold? In other words, are we dumping in hot sodium hydroxide straight from the oven? No, we aren't dumping in any hot sodium hydroxide. So what is delta T of the sodium hydroxide? So it's got to be T mix minus T cold, right? T mix minus T cold. Right?
Yeah. It would be a little warmer because.
So the sodium hydroxide warmed up. And it got that from the cold water. Sodium hydroxide warmed up. It was originally at room temperature, and then it warmed up from the cold water. The cold water warmed it up, right?
Well, no.
No, the mixture one. So that's probably.
You have it?
He said T cold minus T mix.
T cold minus T mix. All right. So the sodium hydroxide was hot and then it cooled down. It was at the mixed temperature and then it cooled down?
Started out.
The other problem was a lot easier because the other problem we just took a hot object and put it into mixed it with a cold object, water, and had some. And so those types of problems are easy. It doesn't have to be hot water. It could be like a hot piece of metal. You take a hot piece of metal, dump it into a coffee cup full of room temperature water. What's going to happen? The hot piece of metal is going to cool down. The cold water is going to heat up, and then we can figure out the specific heat of the metal. And that's this common calorimetry experiment. You know, the hot piece of metal, dump it into some cold water, figure out what the temperature change was, and then get the specific heat of the metal. It could be an alloy or it could be a pure metal. This problem is a lot different. We aren't taking a hot object and mixing it with a cold object, right? We're taking two objects at the same temperature. These two objects at the same temperature interact such that the temperature increases. And so the situation is, and this is what I heard earlier, Keith, what did you say? This is not a object, this is a reaction or a process. And we treat reactions and processes differently than we do objects. So this is wrong. This is only for object. If we have hot sodium hydroxide and it just cools down in this, then okay. But the sodium hydroxide did something more. And so this is the way we look at it, or try to visualize it. You know, on the y-axis we have energy increasing this way. And we'll have sodium hydroxide, solid, plus water, H2O liquid up here. This is a higher energy. This is like gravitational potential energy, you know, higher gravitational energy, lower gravitational. So this is going from higher energy to lower energy. Lower energy would be sodium hydroxide AQ. Sodium hydroxide, AQ, is more stable than sodium hydroxide in water. The funny thing is what happens with the temperature. The sodium hydroxide and water start off at RT, room temperature. Eventually the sodium hydroxide AQ, once it cools down, will be back at room temperature. And so we want to let it completely cool down. When it completely cools down, that releases the maximum amount of heat to the surrounding. And so this is our system. This is what we're calling Q of the system. Q of the system is equal to Q of the, what we call the dissolution process, or the dissolving process. Q of dissolution of sodium hydroxide, dissolving sodium hydroxide. Okay, now where's all that heat going? Into the surroundings. So the heat, and this is the first law of thermodynamics, the surroundings, what is the surroundings now? Okay, now once this has dissolved and all that heat's released, once it's completely dissolved, is any more heat being continuously released? Is this a perpetual reaction? No. This reaction has a finite lifetime, and once it's over, it's over. And so tell me what the surroundings are. Yeah, everything else. What is everything else? The water, the coffee cup calorimeter. Is that it? Water and the coffee cup calorimeter? The thermometer is part of the coffee cup calorimeter. The universe is part of the coffee cup calorimeter. The coffee cup calorimeter is the rest of the universe. Yes. You know, once this is dissolved, then we're left over with sodium hydroxide AQ. It's not just pure water anymore. And so this has got to be Q of the sodium hydroxide AQ. It stopped being dissolved, right, but it's still there. And so rather than having 50 grams of water, we have how many grams of sodium hydroxide AQ?
50 grams of water versus 1.9 grams.
Yeah, so 51.98. Now, is the sodium hydroxide AQ a process or an object? That's an object. And so the sodium hydroxide AQ, that's easy. We have the amount of sodium hydroxide AQ times C of sodium hydroxide AQ times delta T. What is the amount of sodium hydroxide AQ? It's 51.98 grams. What is the specific heat of sodium hydroxide AQ? Unfortunately, we don't know it. Delta T, what is delta T of the sodium hydroxide AQ? That's easy. That's T mix minus T cold. No room temperature, whatever it is. The Q of the calorimeter, what is Q of the calorimeter? The calorimeter is an object, right? And so it's the amount times C of the calorimeter times delta T. The amount is easy, it's just 1. So it's just C of the calorimeter times delta T of the calorimeter. C of the calorimeter, do we know that? Yes. In the previous experiment. We know it. Do we know delta T of the calorimeter? Delta T of the calorimeter is the same as the delta T for the cold water. Cold water and the calorimeter are in thermal contact. And so this is just T mix minus T cold. But what is Q of the sodium hydroxide? Now, this is not sodium hydroxide, an object. This is sodium hydroxide dissolution, a process. It's a physical process, an exothermic process. And so what is it? If it's not an object, what is it? It's a process. So what is Q of the process? What are the equations you have? I gave you 2 equations last time. What are they? One is, Q is equal to the amount times delta H. Or the other is amount times delta U. Okay, what's the difference? Delta H is for our constant pressure. Delta U is for our constant volume. Is this a constant pressure? Are we doing this at constant pressure? Yes. Why are we doing? How do you know that this is constant pressure?
Because it's not in an airtight container.
It's not in an airtight container. Not in a bomb, right? And therefore closed systems can be either constant volume or constant pressure. Do you have a fixed lid or a movable lid? It's still a closed system. And so what are we going to use? Q is equal to the amount times delta H. So unfortunately, we know the amount of sodium hydroxide. It says 1.98 grams, but we don't know this. So we have 2 unknowns, right? 2 unknowns. 2 unknowns means we need more information. So this is what we could do. We could look up delta H, Actually, it's well known. We could look it up in a book. we could look up the specific heat of sodium hydroxide. We have to figure out what its concentration is. We could look it up. This is also known. But that means digging around in reference journals. Which one do you think is going to be harder to find? The specific heat of this specific concentration of sodium hydroxide or delta H for sodium hydroxide dissolution? Which one do you think is going to be harder to find? The specific heat. It's going to be harder to find. And so this is what we're going to do. If that bit of information is not around, what do? You don't give up. You try something. What do you think we're going to try? You know, if a bit of information is not given, this happens. I'll tell you, this happens much more in advanced classes. In advanced classes, oftentimes they don't give you enough information to solve it, and they force you to make a not a guess. It's kind of a guess.
An educated guess.
No, not educated. They force you to make a assumption. They force you to make an assumption so that you can solve the problem. Well, because people will hit this point and will go, not enough information, therefore I can't solve it, therefore I give up. Right? That's not the answer they're looking for. They're looking for, wow, not enough information. Maybe somebody hasn't figured this out, you know? We know that we could look this up, but in cases where that information isn't available, what do? Well, you would do other experiments, right? But in the meantime, before that data is achieved, you could do what?
Assume that C is pretty much the same as the C of water.
Yes, exactly. That's the assumption that they would be looking for you to make. You would make the assumption that hopefully that the sodium hydroxide in the water is so dilute that the specific heat of the sodium hydroxide AQ is about the same as water. Now, having sodium hydroxide in there is going to change the specific heat for sure, so it's not going to be the same thing, but maybe it's close enough. Do you see that? And so this assumption would be much easier to make than this assumption. If we were to try to make an assumption here, what would you assume delta H for the dissolution of sodium hydroxide is? 100 kilojoules, 1,000 kilojoules? It's, yeah, unless you knew a lot, you know, of info, this would be a hard assumption to make, right? Whereas this one might, you know, it's going to be wrong, it's going to introduce an error, but we've already got a bunch of little errors in here already, don't we? And so this one will, you know, alter our confidence in the answer. You know, our answer isn't going to be perfect, but it should be reasonably close, because you wouldn't expect having 1.98 grams in 50 milliliters is going to double the specific heat of water, do you? No. I mean, you'd expect it to change, but probably just a little bit. So this happens a lot less in lower level classes, because in lower level classes you're taught to get the answer, right? The right answer. In higher level classes, the calculations get much more difficult. And since they get much more difficult, you have to make many more assumptions in order to solve them. And so this happened to me. Actually, this happened to me in an engineering class where they didn't give enough. In fact, I couldn't even make an assumption. You know what I had to do? No, it was during a test. I couldn't Google it. What I did was I solved it for an equation and then set the limits. I said probably the lower limit of this variable is going to be here, probably the upper limit of the variable is going to be here, you know, and then set the range of possible values. And that was the answer that they were looking for, that particular thing. And so don't be the blank page person. Stop here, blank page. You know. Chem 1A, hopefully you won't have too many of these. type of deals, but this is common. Do you know your book already does this and not tell you? You know your book makes an assumption in all the, they call these the regular homework. In the advanced homework, they don't make this assumption. In the regular homework, you know what the assumption they make is? Let me tell you, and they don't even tell you. They assume that the heat lost to the calorimeter is negligible. And therefore, in all the book's calculations, in the regular section, there's no heat lost to the calorimeter at all. And then in the advanced section, then they finally say, well, some heat could be lost to the calorimeter. Let's go ahead and calculate that. And so those are the types of assumptions that are commonly made to make the problem manageable. All right, so here, what we're going to do for this is we're going to assume that the specific heat of sodium hydroxide is about equal to the specific heat of pure water, 4.18 joules per gram degree C. If we do that, then what can we get? Yes, one unknown. What's that unknown? Delta H. So we're going to calculate the delta H of sodium hydroxide dissolution. We're going to calculate in 2 units. We're going to calculate in terms of joules per gram. You know, we'll just leave the amount. What was the amount of sodium hydroxide? 1.98 grams. And so we'll get the joules in grams, and then we're going to repeat the calculation and get it in kilojoules per mole of sodium hydroxide. And so just convert grams into moles and joules into kilojoules. And so we'll have both. So this is an example of a reaction is just the same thing. In a reaction, you know, once a reaction's done, it's over. And what are the surroundings? So let's just take a look at one more example before we leave this. And I'm going to ask you what assumption we're going to make for this. The next example is we're going to take this. We're going to take sodium hydroxide, solid, and this time we're going to mix it with HClAq. And so not only is the sodium hydroxide dissolving in water, the sodium hydroxide is going to react with the strong acid, hydrochloric acid. And what do you think is going to happen? A lot of heat will be lost. What are we going to end up with after all this has happened? Sodium chloride AQ plus H2O liquid. And so we're going to call this Q of our system here. The system is going to be a process and a reaction, so we'll just call it Q reaction. The reaction between solid sodium hydroxide and HCl. Would we get a different amount of heat if we took aqueous sodium hydroxide and aqueous HCl? Yeah. Actually, would we get more heat or less heat with aqueous sodium hydroxide? Less heat, yeah. And so this is going to yield more heat. All that heat's going to the surroundings. So tell me what the surroundings are. And so the surroundings are going to start off at some energy here and be popped up to some energy up here. This will be the Q, the surroundings. Q, the surroundings is going up. So to make this equal, this down arrow and the up arrow equal, then we have to say Q, the system is equal to minus. We've got to flip that arrow down. Q, the surroundings. So what are the surroundings? Okay, what we're going to do is we're going to put this into 50.0 milliliters of HCl solution. And this is, let's say this one is 2.01 grams. And so what's our surroundings here?
Q of NaCl plus H2O plus Q of the calorimeter.
All right, the NaCl and the HCl we aren't going to keep separate because that's all one thing. I have it here as H2O, but really this is just what we're going to call NaCl AQ. I just put the water in there to balance it.
Would that be the surrounding?
That would be part of the surroundings. What would be the other part of the surrounding? The calorimeter. And so we got NaCl AQ plus the calorimeter. And so this is a reaction. Now we have two objects. The first object is, how much NaCl AQ do we have? 52.01 grams of this object. And the calorimeter, we just have one of these, right? And so Q of the surroundings would be Q of the NaCl AQ warming up and the calorimeter warming up. These two objects are going to warm up. And we know Q of this is what? The amount times C of NaCl AQ times delta T. The amount we know, right? That's easy. But C, the specific heat of the salt solution, we do not know. But what assumption are you going to make?
Close to.
It's close to water, so we'll just assume it's the same as water, liquid. Delta T we know. Okay, C of the calorimeter is equal to what? How many calorimeters? One times C of the calorimeter times delta T. Do I need to write 1 here? No. Now, if we have Q of the reaction, Q of the reaction is equal to the amount, no, amount of the limiting reagent. What is the limiting reagent? Is it the sodium hydroxide or is it the HCl? I don't know. It's the amount of limiting reagent. Because if all that sodium hydroxide didn't react, well, you already know. All that sodium hydroxide has to react. Otherwise, we have Q dissolution in there. And so it turns out the limiting reagent is the sodium hydroxide. If the limiting reagent wasn't sodium hydroxide and were the HCl, then the HCl would limit how much heat's produced, right? And so fortunately, it's the sodium hydroxide, the Lr, times C times delta T? No, times delta. Is this reaction at constant pressure? Yes? Yeah, I mean, the lid, do you think that lid is like a bomb? Is that coffee cup can withstand build up of pressure or any kind of vacuum? No. And so this is going to be constant pressure, delta H of reaction. And so our unknown here is delta H of reaction, and we could solve for how much heat per gram of sodium hydroxide reacts, or how much heat per mole of sodium hydroxide that reacts. Does that make sense? And in fact, you're going to do both. You're going to get a per gram heat and a per mole heat. Okay, with this calorimetry? Yeah. Okay, bomb calorimeters are a lot easier to deal with. Let's take a look at bomb calorimeter. In the middle of the bomb calorimeter is the bomb. And there's a little platform here where you put your reactor. And then there's some ignition source. And then there's air in here usually. Usually we don't do objects in here. You know why? You put a hot object in here, then you put the lid on the bomb, and then you bolt it on there. These are like grade 8 bolts. You know grade 8? They have different grades of bolts depending on how strong they are. Yeah, tensile strength. So you would have to use high-grade bolts here. Make sure this doesn't explode. But by the time you get the hot object in there and bolted and then submerged and everything else, what do you think that object's done? Let's cool down. And so usually we don't do objects. Objects are easy because objects, do they change their volume much? No, so we could do objects under constant pressure calorimetry. It's very easy. But let's say you put a combustible reactant in here and you ignite it with air, right? Then you're going to need a heavy-duty bomb, because if you combust something and gases are generated, you're going to generate huge pressures here that this bomb has to withstand. Well, the bomb is going to be completely submerged underwater here. And the temperature of the water is measured, not the temperature of the bomb. How come?
Because the heat will still.
Right, because the bomb and the water are in thermal contact. But the problem is water, is a water a good transmitter of heat? Is it an excellent heat conductor? That is, when you put a hot object over here, does that rapidly warm up? No. Water is a very poor conductor of heat, and so we have a stirrer in here. A mechanical stirrer. And so the stirrer is whizzing, creating a current here that mixes the water to minimize thermal gradients from happening. And this thing is encased. This is an isolated, they try to make this an isolated system. And so there's huge insulation here. And so it's isolated pretty much from the rest of the universe. Very little heat should escape from out of the bomb calorimeter into the rest of the universe. And so what do you want to call your system? The reaction. Usually there are combustion reactions that take place here. And so this is our system. The reaction burns. Once it burns, then it releases heat into the surroundings. So what would be considered the surroundings? The surroundings would be okay, the water, the bomb, the whole thing. The whole thing, right? What about the air? Is that part of the surroundings? That's part of the system, right? The system, that's part of it because O2 was required for the system. But when O2 and the combustible reacts, what do you usually form? CO2 and water. Okay, so that CO2 and water, is that part of the system or is that now part of the surroundings? It's part of the surroundings. That's what's left over. That's going to get warmed up. And so the surroundings, this would be our system here. The surroundings would be the CO2 and water that was produced, the remaining air, the bomb, all this other stuff, the water, and this. Are we going to worry about the specific heat of CO2 and water? No, we're going to ignore those. The specific heat of CO2 and water, we'll just say it's close to what it was before. We aren't going to generate that much. And so basically, this is it. This whole thing, everything here is called the bomb. So Q of the system is just equal to minus Q of the surroundings. And in this case, Q of the surroundings is very simple. It's the bomb. Now the system is the reaction. So Q of the reaction is equal to minus Q of the bomb. Okay, what is Q of the reaction equal to? Q of the reaction is equal to the amount times delta H, delta U. Why delta U? It's constant volume, right? Not constant pressure. And so it's got to be the amount times delta U of the reaction is equal to the bomb. How many bombs do we have? 1 times, is the bomb an object or a reaction or process? It's an object, so we'll need the C of the bomb times delta T of the bomb. And so, the bomb starts off at whatever temperature, room temperature, and then increases. And so, 2 things. To calibrate the bomb, we put something that we know delta U, the reaction of. And so we measure amount. We know what delta U is. We can calculate how much heat that should release to the bomb. Once we know how much heat to release to the bomb, we measure delta T. And so C of the bomb is just equal to the heat divided by delta T, in joules per degree C. Okay, once we've calibrated the bomb, then we can put, something that we don't know what delta U is, and then calculate delta U in units of joules per gram or joules per mole. And so bomb calorimetry is easier, right? Because all the heat goes into the bomb only. But we get delta U, not delta H. We'll talk about the difference between delta U and delta H the next time, okay? In more detail.